Imaginary numbers have always seemed confusing. Our teachers implied that they are a useful mathematical abstraction, but only taught us how to use them rather than what they really are and why they work that way. In this video, we will attempt to demystify the imaginary numbers by exploring the intuitive concepts behind them with visual diagrams rather than just formulas. Starting with prehistoric humans before 3000 BC, clay tokens were used for counting things. Our ancestors only needed natural numbers like 1, 2, 3 to describe their world. For example, if Fug caught 2 fish and his son caught 1, then together they had 3 fish to feed the family. As civilizations advanced, people needed answers to more sophisticated problems, such as how to divide land or share a loaf of bread between 2 people. So the Egyptians around 1740 BC developed a new solution: fractions. Fractions filled the gaps on the number line. Eventually, zero and negative numbers were also added, but these were met with great skepticism. The Greeks, for example, despite their advancement in geometry, did not accept zero and negative numbers. After all, how can you take something that isn't there? Eventually, suspicion of zero and negative numbers did fade, as they come in very handy in describing things like depth and direction. Operations on numbers apply to 3 most basic transformations. These are translation, which relates to addition. It moves a point by a given amount by sliding the scale. Scaling or multiplication. This operation moves a point by an amount related to a certain value by stretching the scale. And reversing, which consists of an operation by -1. Multiplying by a negative number stretches the scale in the opposite direction. Humankind's battle with its perception of reality continued with imaginary numbers. We know that if we multiply 1 by 1, the answer is 1. Or, if we multiply -1 by -1, the answer is also 1. In this case, we can say that x squared is equal to 1. But what happens when some rascal inserts a minus sign and writes x squared equals -1? What can possibly be multiplied by itself to yield a -1? It just seems insane. The answer is that this question simply does not have a real meaning. Or does it? Our friend Cora will now help us visualize what happens when we introduce an imaginary number to our number line. As she begins walking forward, we can illustrate her velocity on this line. Multiplying her velocity by 1 keeps the same speed, but multiplying by any other number will decrease or increase her speed. It might be helpful at this point to distinguish between speed and velocity. Speed is the magnitude of the rate at which an object covers distance, whereas velocity is the rate at which the position changes, and that introduces the attribute of direction. If Cora wants to turn around 180 degrees and go in the opposite direction, she will have to slow down, stop, and pick up her pace again going the other way. She cannot reverse instantly, as that would result in an unbearable deceleration similar to a very bad crash. So, what number does she have to multiply her velocity by to turn 180 degrees? The answer is -1. To turn around again, she will have to multiply by -1 one more time. By now, she's multiplied by -1 twice, because she made 2 180-degree turns. But Cora's enjoying her exercise and really doesn't want to slow down and stop for every lap. But if she keeps the same velocity, how can she move between 1 and -1 without going through 0? We just cannot denote such a velocity. It seems impossible, or imaginary. Another way of looking at it is by asking, what number can she multiply by to rotate 90 degrees? We already know that if we multiply by 90 degrees twice, we will have a turn of 180 degrees. So, if we multiply our number twice, it is the equivalent of multiplying by -1. In other words, our number squared is equal to -1, or our number is equal to the square root of -1. Sound familiar? That's our alleged imaginary number, I. Our dilemma arises because the number line is precisely that, a line. The solution is to rise above the situation. By expanding our number line into a number plane, we can now show her velocity as she turns. From our original perspective, however, she seemed to have been walking in place. Sadly, labeling this number imaginary has discouraged many students. Frederick Gauss, one of history's influential mathematicians, once wrote that imaginary numbers have hereto been surrounded by mysterious obscurity is to be attributed largely to a ill-adapted notation. If, for example, +1, -1, and the square root of -1 had been called direct, inverse, or lateral, instead of positive, negative, and imaginary, such an obscurity would have been out of the question. But let us come back to Cora. She could have turned in any direction, but for the sake of convention, a counterclockwise rotation is used to represent I. And continued multiplication with I reveals an interesting property. It cycles through 4 different values, coming full circle. This makes exponents of I easy to figure out. And since multiplication with I represents rotation, it consequently lends itself rather well to the description of motion. But this could be a topic for another video.